Okay, as I alluded to at the end of the last video cast, the average kinetic energy of a gas particle does not depend upon the identity of the gas particle, namely it's on its molar mass, but how rapidly the particle is moving does depend on the molar mass. So we're going to talk now in our final video cast about a quantity that's called the root mean square velocity. This has gone into in much gory and unpleasant detail in the textbook and I think in one of the appendices. If you're interested in the derivation of the root mean square velocity, you can certainly look that up, and I'm not going to hold you accountable for that. You can think of root mean square velocity as kind of an average speed. When you've got a collection of gas particles at a certain temperature, they're not all moving at exactly the same speed. There's a distribution. Some are moving really, really fast, some are moving really, really slow. Most of them are moving in between. That number is called the root mean square velocity. Rachel Braun would probably know what that means. It sounds like a statistics thing. Anyway, so the equation for calculating the root mean square velocity is simply U sub RMS, U being the symbol for velocity, is equal to the square root of 3 times the gas constant times the temperature, all divided by the molar mass. Now, we're going to want to be careful that we use SI units throughout here so things cancel. So we're going to use R in joules per mole Kelvin, and we're going to use the molar mass in kilograms per mole because kilogram is the SI unit of mass. Okay? So this is pretty much basically a plug and chug problem. So the question would be then, what is the root mean square velocity of a helium atom at 298 Kelvin? Annie?
Well, so the URMS is equal to the square root of 3 times 0.008315 83145. 3145 joules per mole Kelvin times 298 Kelvin divided by the molar mass of helium in kilograms per mole, which is 0.004003 kilograms per mole.
Great. That's just the molar mass of helium from the periodic table in grams per mole divided by 1,000 grams per kilogram.
Okay.
Great. So what units cancel in there?
So, units that cancel would be the moles and the kelvins.
So we're left with a unit of the square root of joules per kilogram. That's a pretty bizarre unit.
Well, 1 joule is equal to 1 kilogram meters squared divided by seconds squared.
Very good. The joule is not a base unit in the SI system. It is a, what do we call it, a composite unit or a derived unit? Okay. And it turns out that a joule is actually 1 kilogram times meters squared per second squared. So what you find then, maybe if you just want to do a little unit analysis separately, Annie, and show us that everything works out nice.
So the square root of joules per mole Kelvin times, wait, no, in this case, yeah, you're left with,
Let's make it a, instead,
yeah,
replace the joule with kilogram meters squared per
so
second
your
squared.
kilograms meters squared per second squared divided by kilograms. But that's just but then the kilograms cancel, so you're left with the square root of meters squared per second squared, which is equal to meters per second.
That's really satisfying, isn't it? You start out with this really crazy jumble of different units and you end up getting meters per second, which if you're trying to calculate a velocity is a good unit to be in. And the final value, according to my calculator, is 43.1 meters per second.
So URMS is equal to 43.1 meters per second.
Excellent. Okay. So the last topic I want to talk about is what's called Graham's law of effusion. So let me advance forward and put up my little screen. Okay. So you begin by asking the question, what is effusion? Well, effusion is different from diffusion. Diffusion is when gas particles simply spread out into open air. You may recall the demonstration when I went back into the fume hood, opened up the bottle of ammonia, and gradually over a period of several minutes, people started to smell the ammonia because the molecules are diffusing through the air. Effusion is different. If you begin with a sample of gas in a sealed container, and on the other side of the partition is a vacuum, and you suddenly open up a tiny pinhole, what you will find is that due to the random motion of particles inside the concealed space, eventually they start making their way through and getting into the open container. That is called effusion. Well, it turns out that how rapidly a particle effuses is directly proportional to the root mean square velocity. It's not exactly equal to it, obviously, but it's proportional to it. We don't often calculate the actual rate of effusion of a particular gas, but what we can do is compare the relative rates of effusions of two different gases. Okay? So let's consider two gases, gas 1 and gas 2. We can calculate the rate of diffusion of gas 1 compared to gas 2 simply by dividing their root mean square velocities. That's a pretty ugly equation, and I'm not even sure if I know what the temperature is, but is there any way to simplify that?
Yeah, so all of the three RTs are going to cancel, and then when you take the square root, it's going to end up with 1 over m2 and 1 over m1, so those are the reciprocals. So you flip it, so then you're going to end up with...
Very good. So this is going to be 1 over the square root of m1 divided by the square root of 1 over m2.
So that's just the square root of m2 over the square root of m1.
Very good. So what that tells us now is that the rate of effusion of a gas particle at constant temperature, obviously, is inversely proportional to the square root of its molar mass. So that lets us solve problems like this. Suppose I am comparing the relative effusion rates of hydrogen and an unknown noble gas in order to identify the noble gas, and I find that hydrogen effuses 6.45 times faster than that. How do we use that information to figure out which noble gas we have?
Well, so you have the ratio of the rates, so R of the rate of hydrogen over the rate of your unknown would be equal to 6.45, but that means that the 6.45 is just equal to the square root of the molar mass of X over the square root of the molar mass of hydrogen.
Great. We don't know the molar mass of X because we haven't identified X yet, but we do know the molar mass of hydrogen, so that gets us to one equation and one unknown.
So when you solve for the molar mass of X, you square both sides to get
rid of the square root sign.
6.45 squared times the molar mass of hydrogen is equal to the molar mass of X. And that's just 6.45 squared times 2.016 grams per mole, which is
equal to
X, so X is equal to
83.9 grams per mole.
83.9 grams per mole.
Great. So how do you figure out which noble gas that is?
Look at your periodic table.
Very good. And the periodic table says that the molar mass of krypton is 83.8 grams per mole, which is close enough. So that lets us conclude that the unknown noble gas is krypton. Science is right. The world works.
Everyone is happy.